just let him in.
Okay.
Can you speak up a little, G?
Can you hear me now? How about
Yeah,
now?
you sound great. Yep, that's good.
Thank you.
I'm not seeing the permissions anymore, but let me take myself out of the queue.
Okay, and it's 10 past, so as soon as Sue's back on audio, we're going to get started. So,
We'll give a start to it.
so
Folks, go ahead.
I was just going to say, we'll start with the note well, which all of us have seen, of course, but you know, it's important that you have reviewed this at some point and that you are reminded right now that by participating in this meeting, you are deemed by the IETF to have agreed to all of this stuff. If you don't know what it means, maybe you should talk to your attorney about it. They can advise you. I sure can't.
Okay, let's go to the next screen, John. I got that one. Okay, folks, I send out the status updates at least once a month. I'll update in 2 weeks after the Shepherd reports come in. I have a list. John has a list. We're behind. If you ask for a working group last call, I'll try to catch her in the notes, and I'll send out a list immediately after the meeting to the list. Send me a note. The only important big document is BGP Yang document is starting working group last call. It's going to the Yang doctors first, and the IPR is there. Look, we're going to be short on time today, so I'll be brief. We're going to need interims for several of our discussions, BGP AutoComp, Flowspec, tunnel and caps if we have to consider 6514. It looks like no one's really talked about that. The potential person I had said, nope, he's not using it. IPsec Association. So if there's other topics, let us know. Interims are the way to have a long discussion. IETF has been moved to a shortening discussion due to COVID. Next slide, John. So what if? Can you get, what if Media Echo doesn't work? You have two options. We'll add it to a hot topics or a topical interim. Make a video, send it to the list, or do both. If you don't get a spot, we can add you to a hot topics. See the first statement, hot topics or a topical interim. If you couldn't make a comment via video, use the chat. We'll copy the chat log and send it to the list. If you couldn't hear the presenter, try the YouTube video. If you could not help with the meeting minutes, well, that's not, I'd love to help you the next time for the interim minutes. That's a bit of a news flash. There's a channel. That's it. We have a short meeting. First, okay. I tried to make it 2 minutes or less.
Yep, we got back several minutes for actual meeting.
Yep.
So there's our agenda, and we will now go right on to our first presentation. So, perfect.
Hello.
Hello, we can hear you, although please try to speak up.
Oh, okay. Oh, hello, IDR experts. I'm Wei Wang from China Telecom. I'm going to introduce our draft to you. Its name is Route Distinguisher Outbound Route Filter for BGP4. Next slide, please. This presentation contains 3 parts. First, I will introduce the problems when the routers do not exchange VPN routing information directly and why we propose RDRF. In the second part, I will introduce the solutions we proposed. And the last part is about the further actions of this draft. Next slide, please. Hello?
Oh. Yes, you should see the next slide now.
Oh, okay. In the scenario shown in the figure. PEs establish IBGP sessions with RR to ensure the routes can be transmitted within AS100, where P1 to P4 maintain VPN routing information and RR don't maintain any VRFs. When the VRF of VPN1 in P2 overflows, due to P2 and other PEs are not IBGP neighbors, BGP maximum prefix features cannot work. So the problem on P2 cannot be known. Next slide, please. Now there are two solutions.
Oh, your audio has broken up. She took herself out of the queue, or she fell off the meeting.
Co-authors that can continue on.
Oh, there she is. Okay. Let's try again.
Oh,
Wait, you're yes, good. We can hear you now.
oh, sorry, it's a bad connection.
Understand.
And go on. And if we use address prefix ORF to filter VPN routes, need to pre-configuration, but it is impossible to know which device may overflow in advance. So we define a new ORF type called RDORF. By using this mechanism, VPN routes can be controlled based on source RD and originator. Next slide, please.
Your slide is up.
Oh, okay. When the VRF of VPN1 in P1 overflows, P1 will find out the main source of VPN routes in this VRF. Assuming it is P3, then P1 will extract P3's host address and source RD from BGP update message and generate a BGP route refresh message contains RDORF entry and send it to RR. When RR receives the message, it checks whether it receives the latest entry or not. If not, RR will discard the entry. Otherwise, RR will add it into its ADJ ripout. RR determines whether this RDORF entry should be sent to P3 locally. If necessary, RR will regenerate a BGP route refresh message to send this entry to P3. If P3 receives the message, it will check the entry and add it into ADJ ripout. When the VRF of VPN1 in P1 no longer overflows, it will send RR a BGP route refresh message carries a RDORF entry to remove the previous one. After receiving this message, RR will check the entry. If it receives the latest one, it will remove the associated RDORF entry from its ADJ ripout, and if necessary, RR will regenerate a BGP route refresh message to send this entry to P3. Next slide, please. RDORF can also be used in cross-domain scenarios. In option B and option C scenarios, P1 to P4 are responsible for maintaining VPN routing information in AS1 and AS2. ASBRs and RRs do not maintain any VPN routing information. This makes them cannot know whether the P is overflow or not. So they need the RDOF to control the number of routes. The working mechanism of RDRF is similar to single domain scenario, so I will not repeat it here. Next slide, please. The above is the main content and scenarios of our draft, and any comments on our work are welcome. Thank you.
We have 3 minutes for discussion.
Could you hear me?
Yes.
So, John, could you go to slide number 5? I just a single domain case. I quickly want to ask a question to A. So, here you're saying when PE1 is in overflowing situation, it is going to send a message to RR, and RR will further send it to source PE3, right? But when PE3 initially injects a VPN prefix, that is also meant for PE2 and PE1. But PE2 is not overflowing, right? If we stop at the source, there are many other not overflowing routers are also going to miss the route. How we can address this? Is that clear?
Hello?
Hello.
Can you hear me?
We hear you.
Oh, in our draft, we can the RR will check the source IP address, and it will find this ORF is M2P3, and it will not send it to P2 and P4. So
I think from the draft, it's not very clear to me. These use cases, maybe it's better to explain more in detail. You have any working implementation that you already tried and tested? Could you give us that information?
sorry, it's a bad connection. I can't hear you clearly.
Okay.
Yeah, maybe take it to either try asking your question in the chat, or ideally take it to the email list. Care.
Okay.
Yeah,
sure,
I'll make
thank
it
you.
very quick. Can you hear me, John?
Yes.
Yeah. Good morning, folks. I'll make it very quick. Two comments. One, the back pressure all the way to the PE may not be required. RRs these days have infinite memory and CPU. You don't need to back pressure it. The second thing is, there's a reason why we do attribute-based filtering using route targets, because that brings some level of commonality, which is not always guaranteed by looking at the RDs, and the prefix level filtering is always proven more expensive. So I don't know if this is a good idea. I would vote against accepting as a working group document, but I wait for you to issue a call on this. Over to you, John. Thanks.
Okay, thanks very much for the presentation, and we will now move on to our next one. Giuseppe.
Can you hear me good? Yeah.
Yes.
Okay. I'm presenting on behalf of the other co-authors, and this draft is about the BGP extensions to enable live feed in a SR policy. So next. We already presented this draft during the last interim meeting, and just a quick review of the background and motivation. So the in situ flow information telemetry refers to network OM applications The most popular are inbound OIM, in situ OIM, and alternate marking. And you can see the reference document for these on-path telemetry techniques. On the other hand, we have the SR policy that is identified through head-end, color, and endpoint. And an head-end in general may be informed about the candidate path through different ways, in particular through configuration, by using PCE or BGP. In the context of BGP, and you can see also the relevant draft, the segment routing T policy draft, the scope of this document is to define an extension to BGP to distribute SR policy carrying IFIT information, so inbound on-path telemetry information. So in this way, the idea is to enable both inbound OM and alternate marking or separately when the SR policy is installed. So next. Yeah, as I said, we already presented this draft during the last virtual meeting. We got some feedback both on during that presentation, but also offline regarding the companion document in PC. In particular, the main questions about the applicability. So we clarified that this BGP extension allows just to signal the IFIT capabilities together with the SR policy. So regarding the flexibility of dynamicity and closed loops, closed loop things, these are out of scope because we may use additional function on the controller and network nodes like Young models and so on to address this kind of flexibility and dynamicity. So regarding the generalization to any data plane, since this document, the scope of this document is on SR policy. These IFIT attributes can be extended and generalized also as a sub-TLV for other SAFE and NLA. But just to be clear that now we are focusing on SR policy since the on-path telemetry techniques are becoming mature for this kind of technology, like a segment routing, SRv6. So you can see the reference document that are all adopted document, and also the relevant document for the control plane. So that's why we focused only on SR policy for now. When maybe the IOM and IFIT will become more mature, we can also extend and can generalize also the application. So next. Yeah, on this slide we can see the main purpose of our draft. So you can see the new SR policy encoding structure that this is coming from the segment routing T policy draft, and we just add the IFIT attribute at the candidate path level as sub-TLVs. So in the next slide. Yeah, here we can see the details are the different sub-TLV. So the IOM pre-allocated trace option, the incremental trace option, the directly export option, and the edge-to-edge option. This came from the inbound OM document. So it just we take the information and we build this sub-TLV from the relevant document of the inbound OM. Next. Yeah, the same applies to alternate marking. So you can see the relevant field from RFC 8321 and multi-point alt-mark draft. And also in this case, we are defining the sub-TLV. Next slide, I think is the last one. And yeah, we want to collect feedback about this draft. We also asked the group to evaluate the adoption, consider the anchor adopted work, both in this working group and also the related working group on telemetry. And of course, the questions and comments are welcome. Thank you.
Thanks. We have 4.5 minutes for questions. And of course, we'll take the adoption question to the mailing list.
Okay.
Questions, comments? If not, we'll continue on. Okay, thank you very much.
Okay. Thank you.
Jeffrey, are you presenting? Yeah, good.
Yes, can you hear me?
Yes.
Okay. All right. So I'm here to present two drafts on behalf of my co-authors, Jeff Haas and Srihari. Next slide, please. The first one is about the new type of route targets, bitmask route targets. The idea is that two bitmask route targets match if the result of the logical AND operation of the bitmask is not zero. And that match is used to control route importation and also route propagation when you're using the route target constraint mechanism. I'll quickly talk about the use case for this new route targets. There could be other use cases, but this is the one we have for now. So flexible algorithm is a way to do a multi-topology or network slicing. Basically, you can advertise link attribute information using BGPLS and link NRIs, and you can color the links. For example, a particular link has red and blue link colors, and you can encode. You would put those link information into a bitmask. That is already existing technology. It's just that today they are carried in a bitmask in the BGPLS attributes in case of BGPLS. It could be in other IDP sub-TLVs as well. Now, when we use the bitmask route target idea, we actually pull that out, we put into this bitmask route targets. And let's say that you have a link that has red and blue link color configured. And then the route target will have the 2 bits corresponding to red and blue set in that route target. And then if, let's say if a router cares about that the red and blue link attribute of that particular link, then it would have a local bitmask route target configured with those bits set. With that and with the semantics of bitmask route target, then the existing route targets and our route target constraint and infrastructure will be able to propagate the link NRI towards the router that is interested in this idea. Next slide, please. So we talk about basic idea, it's a bitmask, but then the exact format, it is based on the new BGP community container. Well, it's not new, it's being used in the Y community draft. We would introduce a new type of the community container for bitmask route targets. We also added global administrator and local administrator, and those will need to match as well. There will be a global administrator type and the length, so that you can use AS-based or IP address-based or IPv6 address-based, things like that. And a local administrator is just like what we had before with regular extended community-based route targets. And then following that is the bitmask. Next slide, please. So we mentioned that the bitmask route targets would make use of the route target constraint infrastructure. And obviously, because of this new community container-based new route targets, we need to extend the RTC mechanism. In fact, there was already a spec about extending it to IPv6 address specific route target constraint. The idea is that we just put the okay, I'll skip the idea. The existing problem with that solution is that if the prefix in the RTC membership NRI is not more than 12 octets, then you cannot tell if the route target part is a partial IP address specific route target or a full or partial AS or IPv4 address specific route target. In fact, for that solution, if we use the FE number 2, that problem could have been solved. But even with that, it will not work with the new types of route targets. Got it, yeah. So the proposed solution is that we define a new SAFI for general RTC membership. Next slide, please. So with this new SAFI, the NRI format will be compared to before. We added this parse attribute type. That basically tells you how to interpret the route target part that follows that. For example, if the parse attribute type is 16, you know that it's based on the extended community. And if it's 25, then you know that it's based on the IP address specific route targets. And if it's 34, which stands for BGP community container, then you know that the route target is based on the BGP community container. Next slide, please. So I just presented the general idea. We seek the comments, and also I want to point out that while the new SAFI also work for IPv6 address specific RTC, it is not the intention to replace the existing spec because its current status and possible implementation and deployments. We do want to say that we basically have two ways to do the IPv6 address specific RTC. But we do have a side question for why could we just use FE number 2 for that IPv6 address specific route target constraint. So I'll open for questions and comments now.
G, you're on.
I think I have several comments. The first one is about the bit mask route target. Is this a major use case for the matching of the admin group specified in the draft ints, or you have other use cases about this kind of a route target?
Right now, that is the use case, but obviously it could be used for any use case that where the bitmask based semantics makes sense.
Okay, so then the next comment is about RTC extensions. Several years ago, we have another draft to define the generalized RTC for different type of VPN services, in which we did propose a new SAFI, but that one didn't get adopted. Then we have the IPv6 RTC draft, and in that one, as you mentioned, we have the prefix mechanism, right? But the global administrative field should be a fixed length in that RTC. In that case, it can distinguish the IPv4 or IPv6 RT or the AS specific RT. So I think maybe there's no problem in the existing one. But if you introduce,
okay, sorry to interrupt you. But my understanding is that with the RTC mechanism, even the global administrator part could be a prefix. So when you have that, then it's not enough. But right, and also this new more general situation, then we would need a new SAPI. Thanks.
Yeah, if you think the global field is also part of the can be a prefix, maybe that is another case, and we can discuss more offline. Thank you.
Thanks.
Thanks, Steve. Hi, Bo, you're up.
Hello.
Yeah,
Can you
we
hear
hear
me?
you. Yes, please speak up.
Hello, I have a comment that why not do you want to use like CPOF to do this?
CPO.
Covering prefix ORF, because that ORF extension is not use a new SAPI. So so I want to know why not use that way, because now I see your intention that you also don't have the route don't have AFI and SAPI for specified route. So the receiver receive the route target routes. He don't know which address family want to use the route to let to send routes.
I will have to follow up with you offline, because right now I have trouble understanding what you're describing. We'll follow up offline.
Oh, okay.
Thank you.
All right, thanks.
Hi everyone, this is Tong Li speaking from China Telecom. Our work is about BGP-LS with multi-technology for segment routing based virtual transport networks. Next slide, please. Enhanced VPN as defined in draft IETFs. Enhanced VPN aims to provide enhanced VPN service to support applications' needs of enhanced isolation and stringent performance requirements. VTN is introduced as virtual underlay network with required topology and resource characteristics. Draft IDR BGP-LS SR Enhanced VPN defines the BGP-LS extension to distribute the information of segment routing-based VTNs to external entities, such as the network controllers. Resource-aware seeds are introduced to build resource-guaranteed SR virtual networks. IGP extensions for SR VPN Plus or VTN is under discussion in LSR working group. Multi-topology and FlexArgo can be reused or combined with necessary specification or extensions. This document defines the MT-based BGP-LS extensions for SR VPN Plus, including distribution of VTN attributes to network controller. It reuses multi-topology to build a basic or simplified solution. In this document, considerations about scalability is provided. Next slide, please. An enhanced VPN service is a VPN service with additional commitments such as resource isolation and performance guarantee. It supports the needs of new applications that cannot be provided with traditional overlay VPNs. Virtual transport networks is a virtual network which has a customized topology and a set of network resources allocated from underlying network. To meet the requirement of enhanced VPN services, a number of virtual transport networks needs to be created. VTN provides the required underlay characteristics for one or a group of VPN Plus services. Next slide, please. There are three BGPRS mechanisms in this draft. The first one is intra-domain topology advertisement. MTID TLV is used in BGPRS link descriptor, node descriptor, and BGPRS attributes to identify the topology of the link state information advertised. Topology specific seeds can be advertised using BGPRS SR or SRv6 extensions mechanism. The second one is interdomain topology advertisement. MTID TLV with BGPRS EPE is used to advertise topology specific per peer adjacent seeds, peer node seeds, and peer star seeds. MTID needs to be constantly used in each domain and on interdomain link. The third one is advertisement of per topology TE attributes. One link can participate in multiple topologies. How to advertise topology-specific TE attributes is specified in this document. As we know, the information of network resources associated with a VTN can be specified by carrying the link TE attribute TLVs, which defined in RFC 77552 in BGPRS attribute, with the associated MTID carried in the responding link NLRI. For example, maximum link bandwidth sub-TLV can be reused to advertise the subset of bandwidth allocated to each VTN. Next slide, please. Scalability considerations were included in this draft as well. When a link or a prefix participates in multiple topologies, multiple NLRIs need to be generated to report all the topologies that a link or prefix participates in, together with the topology specific segment routing information. This may increase the number of BGP updates, hence introduce additional processing burden to both the sending BGP speaker and the receiving network controller. Some optimization may be introduced for the reporting of multi-topology information and the associated segment routing information in BGPRS. The mechanism described in this document requires that each VTN has an independent topology, and for interdomain VTNs, the MTID used in each involved domain is constant. Will this bring the benefit and simplicity, and also has some limitations? This means independent topology or route computation for each VTN is needed, even if some VTNs may have the same topology in some domains. Next slide. In next step, feedbacks and comments are welcome, and we will refine the documents accordingly. That's all. Thank you. Any questions or comments?
Hi. So in your last slide, you had some considerations for scalability. I don't know if you have solutions there. If not, the TS draft that someone mentioned earlier when I did my presentation is actually designed to solve some of the problems you pointed out, and the bitmask route target is used to help with that as well. So I think we can talk offline further on possible collaboration consolidation here.
Okay, we can talk the detail on the email list.
Yep. Thanks.
Any other comments? I saw that Zhu was in the queue, but then removed himself. If you still want to say something, G, you're welcome to put yourself back in the queue. Yeah. You're on.
Yes, we have some BGPRS related mechanisms for the network slicing or the information distribution for virtual networks. So we can definitely have more discussion about this in the list.
Great. Any other discussion right now, people? All right, thank you. Yusong, you're on.
Hello?
Hello, we hear you.
Okay, thank you. I'm Yisong Liu from China Mobile. I will introduce the solution of traffic steering use BGP Flowspec with SRv6 policy. Next slide, please. Okay. Firstly, use Flowspec for traffic stereo now is used more and more, especially inter-domain scenario. For the China Mobile network, we face the problem that the traffic of game services is very sensitive to the network latency. And the problem is that how to steer this traffic into the SRv6 policy. So this draft proposed a solution to do so. So next slide, please. For this, this is a example for this solution, and for the original traffic along the blue line in the picture, and it look up in the RT2, and the FIB and in the FIB, the next hop is RT3, and it will through the RT3 to access the RT5. So if we want to adjust the traffic, like 1.1 traffic to through the RT4 to the RT5, so we use the Flowspec route to get that. And in the Flowspec route, we carry the extended community for the redirect IP address for the RT4. We redirected the next hop to the at the endpoint of the SRv6 policy, and the color extended community combine the endpoint. We can match the SRv6 policy. Assume that the controller has delivered the specific SRv6 from RT2 to RT4. So we also carry the prefix seed for the 109:1. So that is the n.dt4 for the RT4. So we may advertise this Flowspec route to the RT2, then the traffic can steer into the SRv6 policy from RT2 to RT5, and we can make the traffic through the RT4 to the RT5. So next slide, please. In this solution, we have no new protocol extension. We just reuse the existing mechanism. Firstly, we reuse the color community and the redirect the next hop. the description referenced in the SRv6 service draft, that the receive route is colored with extended color community, and the next hop, the route will associated with the SR policy, and the next hop redirected by the extended community for the redirect. So the Flowspec will associated with the SRv6 policy. So next slide, please. Secondly, we reuse the prefix seed attribute. In the SR6 services draft, defined the layer 3 service seed, and it can specify the endpoint like the in the example RT4. Well, when the traffic arrived at the egress route like RT4, which behavior it can be, and in this solution, the behavior can be DT4, DT6, or DX4, DX6, etc. Next slide, please. Thirdly, we use the Flowspec components, and that is defined in the RFC 5575 or the base draft. Or all the Flowspec components can be used. Next slide, please. That's all the solution. We will ask for the feedback and comments. Thank you.
Colorage, you're up first. Oh, Colorage fell off while he's getting himself back in the queue. Jeff, you're up.
Hey, this is Jeff Haas, Juniper Networks. I need to look through your draft, but as one of the authors on the redirect IP internet draft, one of our pieces of experience where this is a little challenging to be well specified is since you're specifying more than one community in combination causing the actions to happen, you need to be very clear how this interacts with all the other various redirect features that Flowspec has. That's my comment. Thank you.
Thank you.
Can you hear me?
Speak up, please. But yes, we can hear you.
Okay. But I had a question of how this will work with the interdomain case. Can it work in the interdomain case?
Oh, and please introduce yourself. That's Kalaraj.
Hi, this is Kalaraj.
So, sorry, the sound is not clearly, very clearly.
I see. Okay. Is it better now?
Yeah.
I was asking how does it work in the.
Again.
I was asking how does it work in the interdomain case?
Oh, interdomain case. We will consider in the future draft. Okay.
Okay.
Thank you. Thank you.
Okay. Anyone else? Okay. Thank you very much.
Thank you.
Oh, am I going to miss someone? I have Kalaraj next, but I think we're supposed to be Path MTU first. One moment. Sorry. There we go.
Hi, this is Shu Ping. I'm going to present this BGPRS extensions for advertising from MTU. Next slide, please. First, about the motivations. And in MPRS, and we know the path MTU can be signaled via the protocols like the RSVPTE. But in SR networks, there is no such negotiation mechanisms for the path MTU. And basically in the SR network, the SR information is reported by the BGPRS, and then the ICN controller can calculate the SR path based on those information. And we also know that when we start pushing the seed, either a label or IPv6 addresses into a packet, the packet size is going to be increased. And once the packet size exceeds the path MTU, the packet is going to be dropped in IPv6 or fragmented. And from the operators, we learned that, and when using the least line over the multiple domains, the MTU needs to be learned in order to avoid the packet drop. And so in this draft, in order to enable the controller to calculate the path MTU, so we specify the extensions to BGPRS to carry the link MTU. Next, please. So here is the deployment scenario. In the RFC 7752, it already specified the collection and distribution of the LSNT information. So it's basically, it's the router will maintain the LSDB, and then so via the BGP process, and it will get the information from this LSDB and distribute it to the consumer, either directly or via like a dedicated RR. So the link MTU is going to be collected. It's going to be delivered in this process of collecting the RSNT and by the BGPRS. And we already know that in the RFC 7176, it already specified the EZs mechanisms and extensions for the link MTU sub-TLV. Okay, next, please. So here, and again in this RFC 7752, so it already defines the TLV that map the link state information to the BGPRS NLRI and attributes. So in this document, we will define a new sub-TLV for the link MTU and then add it to the link attribute TLV. The format is like this, and we actually reuse it. And then so whenever there is a change in the MTU value, and the BGPRS will put the new value into this TLV, and then the controller can recalculate the path MTU. Next, please. So the changes from the last version, and here we're actually following the comments from last time, and that's about the IGP or easy use extensions. So before, and we have a mechanisms and another draft for collecting the link MTU, and in this version, and we change it to, so actually we refer to this existing RFC 7176 to specify the EZ's extensions for this link MTU. Next, please. So next step. So basically, it's all about this diagram at the bottom. And so the link MTU are generally collected via the EZ's or IGP mechanisms, and then it will be delivered to the controller via the BGPRS. So after the calculation inside the controller, the path MTU will be delivered to the network head end. So here, correspondingly, so for delivering the path MTU, we have the draft. It's already adopted in the IDR. So that is for to define the extensions to BGP and to distribute the path MTU information within the SR policy. And here, the draft we are presenting actually specifies the extensions to BGPRS to carry the link MTU. So here, and we would like to call for adoptions for this draft. Thank you. That's all. Any questions?
We have 4.5 minutes for questions. Okay, done.
So I think the ISS draft that you referred to is actually a trill draft, right? I'm not sure
Yes.
if it's same as ISS. That's one.
Yes, that.
And the second question was, what exactly would this MTU be? Is it a link layer MTU? It's an IP MTU. Does it count MPLS? Any overheads? I think that would also help.
Okay, cool. So the first one is from the trill draft, and that is actually from the comment. I think is from chairs, and as I already presented, so we have another draft on this, but it was pointed that we could reuse the one in that draft. So that was for trill. Yes, that is true. And for the second question is here the MTU, and basically we meant for the link MTU, and in the existing RFCs. So, for example, the RFC 8201, and there is already the link MTU, the definition for this link MTU. That is the minimum, the maximum text size that can be carried within over the link. So, and that actually depends on the packet size. So, and then for different data plane, it has different meanings. And for the SR MPRS, and SRv6, there will be different way to calculate. So for the MPRS, there is another draft, so we can refer to, because that will plus the IP header plus the payload and then the label. So they have different ways to calculate. And in the existing RFC, the link MTU generally in IETF means the IP MTU. Okay, hope. So we realize that there will be, it needs to clarify. So probably we would add the terminologies accordingly in the draft to for the further clarifications. Thank you.
We had Sue next, and then Ketan, if you want to follow up, we still have some more time.
Jeff, I'll take mine to the thing. It was a question for Ketan on what he said. I'll let Ketan go ahead.
Okay, well, he put himself in the queue and then he took himself back out, so I'm not sure if he wants to say anything. Ketan, please go ahead.
Thanks for the clarification. I don't have anything further. We can take the discussion on the list.
Okay, thank you.
Great. Thanks very much. Let's see.
Okay, thank you.
Thanks. Colorado.
Hi, everyone. Is the audio okay, John?
It's perfect.
Okay, cool. So today I want to introduce this new draft. It's called BGP Classful Transport Planes. I'm presenting this on behalf of my authors who are listed in the draft. Next slide, please.
Oops, hang on, sorry. There.
Yeah, so what is the problem being solved? So any network which is a BGP-free core, it has multiple domains, and a domain has intra-AS tunnels. And those tunnels could be classified into varying TE characteristics based on what are their properties. We can just call them gold, silver, bronze. And these tunnels could be between multiple destinations. There could be multiple tunnels to the same destination, and different protocols could be creating these tunnels. And these tunnels could also be extending multiple domains. They could be interdomain tunnels. And it would be good if we can preserve the TE characteristics end-to-end for the interdomain tunnel. And irrespective of whether my service endpoint is in the same domain as I am, or it is in the adjacent or a domain beyond it, if the service routes are able to resolve or put traffic over these tunnels of a certain T characteristics such that the T characteristic is preserved end-to-end, that will be good. So the service routes want this behavior where they want to be able to resolve over a tunnel of a certain T characteristic with option of falling back to, let's say, a best effort tunnel. So these are the requirements. And how do we achieve this? How do we extend BGP to signal this piece of information so that it can get done in the intra-AS case and the inter-AS case? So that's the problem statement. So here we show you an interdomain network, which has like 3 domains. And each domain is classified by where we do BGP next hop self. So we show 2 ASs, AS1, AS2, and AS2 has 2 regions inside. And at ABR22, we are doing BGP next hop self. And this is like a BGP LU network. It's like a classic option C. And we see that in each intra-AS domain, we have gold and bronze LSPs, the LSP1 and LSP2. And there is a best effort tunnel, LSP3. But when we advertise these reachability to PE11, that is 1111, to the other domain or across to BGP, we will be able to advertise only one label. And so we either swap to LSP1 or LSP3, whichever one we pick in the intra-AS domain, or it could be a ECMP of all of them. So eventually PE21 is not having visibility of each of the individual classes of tunnels, and he cannot put traffic on each of these individual tunnels separately. And that applies to any of the services that are at PE21 or even ASBR11. Next slide, please. So how do we solve this, and what are the constructs we are introducing in BGP-CT to solve this? So when we say we are grouping the tunnels using TE characteristics, so that we are calling it as a transport class. So any tunnel can be classified as belonging to a certain transport class. And these tunnels could be signaled by RSVP or SRTE or FlexAlgo or any different tunneling mechanism. And we identify the transport class on the wire using a route target. It's called a transport class route target. It's a route target extended community, which is just having a new format. It carries the transport class identifier in it. And the transport class identifier is just a 32-bit integer. So it's a way of advertising the routes to the other domains and saying these tunnels belong to this particular transport class. And for the case of there could be multiple tunnels to the same destination, we just use the route distinguisher to distinguish them and to advertise them without path hiding, and also allowing identifying the originating PE. So these are like mechanisms of 4364, that's plain BGP VPNs. We are reusing it at the transport layer here. And for extending the tunnel to other domains while preserving the same transport class end-to-end, we need to do 2 things. One is option C style procedures to do the label swap. And we need to resolve the protocol next hop of the received route using a set of routes which belong to the same transport class. So basically today what we would do is we would resolve it over any tunnels that are available, so which will include best effort tunnels, gold tunnels, and bronze tunnels. So here, because we are giving an identification of these tunnels belong to a certain transport class, so the receiving speaker, he organizes the tunnels of a certain transport class in a separate database. And for resolving routes, transport routes, which are received using that transport class route target, he uses only these tunnels. So this allows to preserve the transport class end-to-end across domains. And this information is being used in a new BGP family, which is nothing but a new SAFI. It's SAFI 76 called Classful Transport. And this address family, it follows 4364 procedures. And there will be IPv4 and IPv6 versions of this so that we can carry v4 tunnels and also v6 tunnels in the same way. And the service routes, so far what we talked about was at the transport layer. Now with the service routes want to resolve using a concept called a resolution scheme. What is a resolution scheme? It's basically saying that we want to resolve over certain transport class with an option to fall back to a different transport class. So what a resolution scheme means, it's a kind of local definition of the speaker, but the service route carries something called a mapping community, which indicates which resolution scheme that service route wants. For example, a service route can have a mapping community which can say, I want to resolve over gold and please fall back to bronze. And this mapping community is nothing but a regular BGP community. It could be any community, but we could also have communities like the extended color community, which is already in use. And it could carry the transport class identifier, which could automate things and reduce configuration. Next slide, please. So here, the same network that we saw before, we're just showing an example of how we are able to have PE21 choose based on the VPN prefixes that are received with community gold and community bronze. So those community gold and community bronze are the mapping communities. And they will resolve over respective the gold LSPs or bronze LSPs. And the reachability to the gold LSPs or bronze LSPs, basically the LSP in the first domain in AS1 is advertised up to PE21 using the right transport class route target so that they are visible to PE21 with the right transport class. Next slide, please. So this is just a sneak peek of the PCAP. So you can see that it is very similar to an L3 VPN update. You have the RD, you have the route target, and it just instead of 1/128, it's just 1/76. So it's just to show how we are reusing L3 VPN family, and everything else will follow. Next slide, please. So the advantages here, so we see that each intra-AS domain, there could be various different tunneling protocols. It works with any of them. And also at the service layer, it works with any of the service families for V4, V6, L3 VPN, even Flowspec. So Flowspec also, we can consider it as when we receive the redirect IP next hop with extended color community, we can resolve it over a tunnel of that particular transport class. So it is in a layer which basically is doing a change, and all the transport families plug into it and all the service families plug into it seamlessly. And so it's like a natural extension to any deployment which has already BGP-LU option C. And we are reusing the BGP VPN technologies as we already talked about. And as a side effect of that, we can reuse RTC also. And we can, by virtue of that, get on-demand next hop. For example, we could, yeah.
There's somebody in the queue. Do you want to take questions as they come, or do you want to hold them for the end?
Okay, yeah, I can take it now. Hey, Robert.
Robert, and by the way, please remember to announce yourselves.
I think Robert dropped off.
Maybe he fell off the queue. If you want to still make a comment, Robert, go ahead and add yourself again, and I'll accept you. Oh, there you are. Try it again. I had this problem during the test session, Robert, and I was using Safari, and I stopped using Safari, and the problem went away. While you're debugging that, please, Kalaraj, continue.
Yeah, I just have one more slide. Maybe I'll finish that and wait for the question. Okay. So using the route target constraint, we could have a mechanism such that the ingress PE, when he receives the service routes, L3 VPN routes, he can discover which protocol next hop he wants and what are the transport classes he wants. And he can request the next RTC routes for those next hops, so that now he gets the BGP CT route for only those next hops. So this way, because of the RTC is in use in both the layer service and transport, we'll be able to make sure that the ingress PE is able to get only the protocol next hop that he is interested in and not everything. Next slide, please. So this is just a note on why we had to go with a new address family. Why not just reuse or hack existing families like LU, SRT, or L3VPN even. So the main thing was like color is an adjective. It's not a noun. So carrying it as an attribute made more sense. And the route target already in the L3VPN world, we use it like colors. It's like membership. So that is why we modeled the transport class as a route target. And RD is a route distinguisher, end to end. At path ID is like per session scope. It's like RD is having a different RD will cause a new label getting allocated, but at path ID is like an end result. If you have a new label to advertise, then we use a new at path ID. So I think both of them are required in this mechanism. Either one of them is not enough. So we use the RD as an identifier, and whenever we cross AS boundaries where you have multiple ABRs, just like the option B L3VPN case, we use at path ID. And use of RTC allows for ODN, as we already saw. And so there was initially a temptation to further overload L3VPN family to carry the transport routes. And to point to be noted that is even today we do that when we use Courier's Courier. In Courier's Courier deployments, we carry transport routes in L3VPN family. But it then figured out it may be operationally simple and required to actually have a different L3VPN-like family, which is playing in the same level as LU. So the reasons are because the route propagation path for transport routes is different from service routes. They have to do hop by hop instead of going on a multi-hop eBGP session. So separating them out in a different family is good. Also, behaviors like per prefix label can be given for transport routes, which are like lower scale. So if we separate out these transport routes in a new family, it's good in that sense also. So thus we have this new SAFI 76. It's just a transport family that can signal transport class also. So it will kind of have all the properties of BGP-LU and a little more. So that's the end of the presentation. We would like to request comments on the list and even here.
Okay, anybody can put themselves in the audio queue. I also saw, okay, Sue, please go ahead.
John, I'm reading Robert's question. Today, a transport class can be embedded in the SID. Here we are opening up to explicit signaling. I understand you may want to support our RSVPE, but I'm not sure if this extra complexity is really needed. Second question, I like the new SAFI separation. If we go for that, I recall that BGP 3107 had discussions about it too. Just not sure if we need it if we are up to SR everywhere paradigm. That's his comments. Hopefully that was helpful, Robert.
Kalaraj, would you like to respond to that at all?
About the thing about SR everywhere, so I don't know. We just want to create technologies which work with any tunneling. It doesn't have an assumption of a particular type of tunnel. So it works with SR also, but it works with other deployed technology that we have today, or even new type of tunnels that may come in future. So that way, I think it is good to have a layer which is not having assumptions about any specific transport tunnel or a service family. And about the 3107 new family, I don't know whether you're talking about LCU. That is what I was saying, why we don't want to reuse LU or introduce a color again in the NLRI, because color ideally belongs as an attribute because an adjective is not a noun.
Okay, and I think Robert still can't use his mic, so any further discussion probably should go on the list on that one.
Okay.
G, you're up.
Yeah. One quick question. I see you mentioned, I think you mentioned that SR policy as in the draft also, but actually SR policy has a color as a part of the NRI, and you have in some cases you need to transfer SR policy between SR policy and your transport class. So do you think there should be in a line?
Yeah, so the SRT tunnels, which are received with a certain color, so that color is kind of the transport class of that particular SR tunnel. So we, when redistributing, so to say, this SRT LSP into BGP-CT, so we will create a transport class route target which carries that particular color so that it seamlessly fits into the existing deployments of SRT. And for the intra-AS case, BGP-CT itself, the family itself will not be required, but the resolution will happen in the same way, where the service routes are getting the extended color community with the color, and it will resolve over a protocol next hop with that particular transport class, which is identified by the color carried in the SRT tunnel.
Okay.
Does that answer your question, G?
Yeah, I think I will check more about the draft. Thank you.
Okay.
Okay, anything further? Okay, well, through some miracle, and by miracle, I mean thank you, speakers, for all sticking to your time slots. It worked really well. We do have some extra time. We have one request for a presentation that we couldn't fit in, and it seems that we can. So, Jeffrey, please put yourself in the audio.
Hello?
Yep.
Okay, great. So I'm here to present some proposed extensions to the tunnel encapsulation attribute that are proposed in this BGP multicast controller draft. Next slide, please. So the idea of controller signal multicast is that the controllers will calculate the multicast tree and then program the routers on the tree for this multicast forwarding state. Now, I'm not going to talk about how that signaling is done. I just want to focus on the representation of the forwarding state using the tunnel encapsulation attributes. So TEA, tunnel encapsulation attributes, it can include a list of tunnels of various types. When it's existing technology, when it is attached to a unicast route, the matching traffic will be sent out of one of the listed tunnels. Now, for multicast, we're proposing some extensions to that TEA, and in particular, when a TEA is attached to a multicast route, then the matching traffic will be replicated out of the listed tunnels. It's not that you will be sending traffic out of one of the tunnels. You're sending the traffic out of all the listed tunnels. So that's the main idea. And we we propose 2 new tunnel types and a few sub-TLVs for multicast purposes. Next slide, please. The first new tunnel type is any encapsulation tunnel. Today, all the tunnel types are associated with a particular encapsulation type, for example, IP in IP or MPLS or whatever. And now this new one just means that I don't care what kind of tunnel it is. I only need a way to get to the remote endpoint address that is listed in the sub-TLV. There are 2 examples in this. One is for native IP multicast forwarding. IP multicast traffic from upstream nodes replicated to a bunch of directly connected downstream nodes. Now the TEA will list a bunch of any encapsulation tunnel. Each tunnel will have the downstream's interface address encoded in the remote endpoint address. In remote endpoint address sub-TLV. And then when you send that route with that TEA to the upstream router, the upstream router will go through the tunnel, will know that, okay, I need to replicate traffic out of these specific interfaces. Well, no, I shouldn't say, yeah, in the IP multicast case, that will be the interface address. So now, another situation is for both native and labeled multicast forwarding, where traffic needs to be tunneled from upstream node to non-adjacent downstream nodes. But again, it does not care which tunnel you use. Any available tunnel, be it MPLS or SRTE or GRE or whatever. So any tunnel type or tunnel instance can be used. So that's where this new tunnel type comes into play. Next slide, please. Another tunnel type we call a load balancing tunnel. Consider this situation. You have m ways to reach a downstream node from an upstream node. And the controller says that out of those m ways, I want you to use of the n ways to send it to downstream node. Now, in this case, you cannot use the any in-cap tunnel, because if you do so, then all m ways could be used. So for that purpose, we use this load balancing tunnel. The load balancing tunnel also lists a few tunnels, just like the TEA itself. So this load balancing tunnel itself is a member of a TEA that is attached to the multicast route. So now when the traffic comes in and matches the particular routes with this TEA, the traffic will be replicated out of all the member tunnels of the TEA. One of the member tunnels could be a load balancing tunnel. So for that one, for that particular member tunnel in the TEA that is load balancing tunnel, then only one of the member tunnel is in the load balancing tunnel will be used to send traffic. Next slide. This is a new sub-tier we were proposing. So if you consider unidirectional multicast traffic, the forwarding state will include upstream and a bunch of downstream. And encoding downstream in the tunnel encapsulation attribute is quite natural. But it turns out that encoding upstream information in the TA is, in my view, is also quite reasonable and convenient to do so. All you need to do is just to add a sub-TLV, we call it the RPF sub-TLV. That means that this tunnel in this TEA is actually for upstream and for incoming traffic. So even though we started with unidirectional multicast traffic, this is also applicable to bidirectional case. In the bidirectional case, the forwarding states for each tunnel will include the forwarding state will still involve upstream node and bunch of downstream nodes, even though you would both receive and send traffic from any of those upstream or downstream nodes. Still, we can one of the tunnels will carry RPF sub-TLV, indicating that that tunnel is for upstream purpose. Next slide, please. And then come to MP to MP MPLS support. So today, an MPLS tunnel can include the label stack sub-TLV for sending outgoing traffic. Now, when it comes to MP to MP MPLS tunnel, we would need another label stack for incoming traffic. So we define this new sub-TLV called incoming label stack. It's just like the existing label stack sub-TLV, but with a different type. So in case of this MP to MP, a tunnel will include both types of label stack, one for incoming traffic and one for outgoing traffic. So we started with MP to MP, but now we can go back to P2MP. This new sub-TLV is also used for P2MP for the upstream, because in the P2MP case, the upstream tunnel for the upstream node to the downstream, you would also need to know the information on how to receive traffic. So that's where the incoming label stack is used in a tunnel with the RPF sub-TLV. It's used for incoming traffic. Next slide, please. The final sub-TLV we're introducing is, we call it the tree label sub-TLV. Again, in case of MPLS tunnel, the label stack sub-TLV for the outgoing traffic will include both the tree identifying label and the transport labels. So the tree identifying label is important so that the downstream node knows that which tree it is for. And the transport labels are used to get to the downstream node. If you use MPOS tunnel, that works. But what if you want to use any encapsulation tunnel? You say that I want to get to this downstream node. I want to specify this tree label, but I don't care what transport label stack you want to use. The controller does not specify that. So in that case, we will just put this tree label sub here. Now, the receiving router of the, will construct the outgoing label stack as following. You push the tree label if the subTLV is present. The subTLV for the tree label is present. And then you put the transport label stack. The transport label stack can come from two ways. One is that you have outgoing label stack subTLV for the tunnel. So that's the label stack, transport label stack you use. Or if you don't have the label stack subTLV, then you can just do a lookup of the remote endpoint address. That will give you outgoing label stack for transfer purpose. Now you have the entire label stack for both tree label and transport label. Next slide, please. Next one. So in summary, for multicast purpose, we propose two new tunnel types: any in-cap tunnel and load balancing tunnel. And we proposed three new sub-TLVs: RPF sub-TLV to indicate that this tunnel is actually for upstream, and incoming label stack sub-TLV to indicate that this is for incoming MPLS traffic, and the tree label sub-TLV to indicate that this label is to identify the tree. So the draft BGP multicast controller draft is its home is best, but obviously the proposed changes to TEA needs to be blessed here. So that's why I'm presenting here and seeking comments. And if this is acceptable, reasonable, and we would like to request early allocation because there are already ongoing trials.
Okay, thanks. Yeah, so I'm putting myself in the queue, and anybody else who wants to make a comment, please go ahead and add yourself to the queue. So I got a few things, very interesting, thank you. So one thing is kind of just an observation, which is it seems to me like the any NCAP is, if there were such a thing as a BGP route with with multiple next hops, would you be able to use that just as well? I mean, there isn't, but it seems like what you're trying to do is push in a route that says, here I've got 20 next hops for you, and I want you to use all of them.
Right, but in some situations, I don't want, the controller does not want to specify which one to. Maybe the controller does not care.
Oh, sorry, it's the load balancing tunnel or load balancing, not the any NCAP. The load balancing one is, no, that's not it either. Okay, I'm sorry. I guess just the whole idea is that the controller wants to say, I want you to replicate across all of these next hops, right? This is the basic thing of saying, I'm going to give you 20 tunnels and I want you to replicate across all of them, right?
That's a top level tunnel encapsulation attributes. That does not involve load balancing tunnel yet. So you just say that basically the controller says that I want you to replicate traffic out of this 20 downstream nodes, and that 20 downstream nodes is basically represented by as a tunnel. Each downstream node is represented as a tunnel, right? So let's say for one particular downstream node, there are 30 ways to get to it, and the controller says that instead of using any of those 30 ways, I want to use I want you to use one of those 20 ways. So the controller will list those 20 ways to reach that particular downstream node. So that's where the load balancing tunnel comes in. So
got it. Yeah, sorry, I mixed up a couple things.
Okay.
So yeah, the first observation is just gee whiz, if we did have, which we don't, if we did have a way to represent 20 different next hops, probably you would have used that instead of the TEA attribute. But it's not a criticism, it's just an observation. Okay, second thing is seems to me like the load balancing tunnel is something that's not whose utility isn't restricted to just multicast, right? It's like we do load balancing in unicast all the time, and you can imagine a controller wanting to program that.
Correct. It's just that today the TEA itself is already the load balancing concept. It's best not necessarily load balancing, but it's basically up to the sending route to decide which tunnel to use based on the situation. So the load balancing concept it is introduced for a multicast purpose. It could be used for non-multicast situations, but it seems that the existing TEA already covered that situation. But on the other hand, any in-caps tunnel itself, that can be used for unicast as well. It's really the downstream BGP speaker says that instead of using BGP next hop, protocol next hop in the update, use this endpoint in the TEA. And I don't care how you get to me, and as long as you can get to this this endpoint.
Right, and then my final point is the thing you said about programming incoming packet handling slightly freaked me out, in that the whole model that tunneling caps mainly follows is I'm sending you to the head end of the tunnel, not the tail end of the tunnel. Like there's no concept of sending a tunneling cap to the tail end of a tunnel. So it's a little weird. I'm not saying it won't work, but it's not really the model that the spec uses.
When you say tail end, what can you elaborate on that part?
Well, when you've got a unidirectional packet flow, one end is the head, or the ingress end, and the other end is the tail, it's the egress end. So we do everything, we send the tunneling caps towards the ingress end.
Right. Here, the BGP route is sent to every router on the tree. So including the tunnel ingress, the replication points, and the tunnel egress. So for the routes sent to the tunnel egress, the tunnel encapsulation attribute will just include an upstream tunnel.
So it's an upstream label allocation?
No. The upstream allocation, label allocation, is really for the service label. It's not for the tree label itself.
But then you should be using
label allocation is not relevant here.
But you should be using a reserved label then, which is already statically carved out.
No. So this is actually getting into the context of context beyond the tunnel encapsulation attributes. I can try to say it this way. So the label that identifies the tree, it could be two situations. One is that the label itself is downstream. Well, it's because we are talking about controller signaling. So that label is determined by the controller. The controller could say that every router on the tree will use the same label. So that same label will be coming allocated by the controller from a common sRGB case.
Yeah, so it's a statically covered out case.
Right. Another situation is that somehow the controller learns that every router's address space that reserved for multicast purpose, and then you could just allocate a label from that every router that relevant router's local address label space. It depends on what the controller does.
Yeah, but that's also a statically carved out case, I think.
Yes.
So my comment was to John's first and second comments, where we were saying that we don't have a way to carry multiple next stops on the same route. So there is a draft about multi-next stop attribute, which try to do that. It's not made progress, but I specified how to carry multiple next stops on one BGP route, which can be used instead of add path, and can be used for upstream label allocation also with MPLS routes, in conjunction with private MPLS namespaces. So just to state that. Thank you.
Actually, I have a follow-up comment about that approach. Instead of using multiple next stops, could we just use tunnel encapsulation attribute for that purpose? So you attach the tunnel encapsulation attribute, and in there you basically just list multiple tunnels, one for each desktop address you want to use.
One for each tunnel next stop address. So tunnel encapsulation attribute, the way I see it, it is about saying to a particular next stop, how do you want to go? So it's like giving additional encap information and etc. about next stops that you already know. So the multi-next stop attribute is just giving you a way of carrying multiple next stops. And it may say things like, this is the way I want to do load balancing, like, or unequal cost load balancing, or this is your FRR leg. These are the order of FRR that you want to do. So it's slightly different. You can use tunnel encapsulation attribute in conjunction with that multi-next stop attribute, where you can say each of the next stops specified in the multi-next stop attribute, how do you want to reach what tunneling, whether you want to restrict the tunneling to GRE or MPLS or whatever. That's the way I saw the dependency between these two drafts.
Okay. Yeah, I need to read your draft first. Yeah. Okay. Thank you.
Sure.
Okay, guys, and let's cut the comments now because we have 3 minutes left in our allocated time. So, Sue, do you want to? Thank you, Jeffrey, by the way. Sue, do you want to make any final comments?
The only draft adoption calls I have are draft Quinn IDR as our policy IFIT, draft Sue IDR BGPLS path MTU. Did I miss one? If so, please put it in the chat window or so that I can make the right calls. That's it, John.
All right. Thank you very much, everybody. And thanks again to all the presenters and the questioners for helping us stay on time and even early so we could fit in our extra talk. Really appreciate it. Okay, we possibly will see you at some interims, as Sue mentioned at the beginning of the hour. And if not that, then we'll see you online for the IETF that will formerly have been known as Bangkok when we get around to that stage. Just a guess. Goodbye.